Okay. Um, I'm not sure what's. Oh, okay. I'm looking at the room from the other direction. Um, Down there. So, um, all right. Um, okay. Just a reminder of upcoming assignments. So, um, so actually, what's covered this week will go on to homework 7 that's due next week. So I'm going to continue with that tonight, getting further into numerical integration. Okay. All right. All right. So quickly, we're leaving off. Okay, that the idea is that the integral, definite integral of some function f of x over ab is being approximated by the exact integral. Whoops. Of some polynomial Pn minus 1 of x of degree n minus 1 that interpolates f at selected points. And that exact integral is given by, okay, the sum of values of f at select points called the nodes, and multiplied by selected values wi that are called the weights. The weights, or sorry, the nodes. Right now, I haven't said anything about how we choose the nodes. That's really the subject of today. But they're points chosen from the interval AB, naturally, and since the integral only deals with the values of f between a and b, and then the weights are the integrals of the Lagrange polynomials on AB. Although what we're going to be doing generally is not actually computing the weights in this way explicitly. I'll be giving some cases where the nodes are chosen, then I'll be able to tell you like specific numbers or formulas what the weights are. So that's already been worked out. But one of the homework problems will consist of writing MATLAB code that, given these nodes, go ahead and compute these weights. And the MATLAB polynomial functions make that a very straightforward process because polyfit can be used to get the Lagrange polynomials in the first place. Then polyint lets you compute the antiderivative of a polynomial. And then polyval can be used to plug in the limits a and b. Okay, so now this process was called interpolatory quadrature. So what we're going to look at today or tonight is how do we choose the nodes, and once that choice has been made, then how can we assess the accuracy of this approximation? So in the case of polynomial interpolation, we do have an error formula. So we will actually use that to come up with an error formula for that was done for numerical differentiation. It'll be useful for numerical integration as well. Okay. Now, The simplest and very widely used approximate integration schemes are called Newton-Cotes rules. And I was interested to find that when I had read about these some time ago, but it was actually primarily Cotes, the lesser known of the two, who really did most of the work in developing them. So it's good that his name got attached. Because just because something is named after a mathematician doesn't mean they had anything to do with it. And the most famous example I can think of for that is something you learn about in linear algebra, Gaussian elimination. So Carl Friedrich Gauss, an incredibly prolific mathematician, arguably one of the greatest of all time, well, some might say the greatest. So there are a lot of things he legitimately did develop. Gaussian elimination is not one of them, because he lived just a few centuries ago, whereas it's been known that something along the lines of Gaussian elimination has been carried out for thousands of years, for instance, by the Chinese. So how his name got attached to it, I remember hearing some presentation about this. I don't remember the details, unfortunately, but someone just called it that, and it sticks. People don't name, or you hope anyway, people don't name methods or other mathematical entities after themselves. There is no Lambert's method out there unless somebody else does it. My own advisor refused to have one of his own methods named after him. Once he passed away, it was done. So it's a funny business. Okay, so what are Newton-Cotes rules? So first, the general idea is the nodes are equally spaced within AB. And there are two classifications of Newton-Cotes rules. Okay. First, there are most of the rules you'll see are closed rules, and that's where the endpoints A and B are included among the nodes. And we'll see one example of open rules. So A, B, not included. All right. So in other words, only points within the interior of the interval AB are actually used as nodes. But whatever nodes you end up choosing, they must have equal spacing between them. Where before in this class has equal spacing been a bad thing? Yes, polynomial interpolation. What's the example? What's it called? Runge's example. So 1 over 1 plus x squared, you interpolate by a polynomial with equally spaced points, and it goes badly. Championship points are used instead. We will see that here too, equally spaced points can be a problem for that exact reason, because we are again dealing with polynomial interpolation. But people like equally spaced points because they're so easy to work with. Okay, so what I'll do is describe there's 3 rules in particular that are the essential ones. And because all of them use a small number of nodes, we'll see 1, 2, or 3. So with a low number of nodes, equal spacing isn't really going to be a problem.
What exactly are the nodes? Are they points or are they just x values?
Both. They are points along the x-axis. So because since we're evaluating f at points in AB, like I think Riemann sum, we're choosing specific points in this interval. And you'll see what I mean when I actually describe these methods and what the nodes are. Okay. So the first one is called the midpoint rule. Okay. So it has one node. So now keep in mind, the nodes are chosen from within the interval AB. So it is, predictably, the midpoint, A plus B over 2. And that is the only node. And because there's only one node, there's only one weight. And that would be B minus A, the width of the interval. One thing to keep in mind is that in general, certainly for any interpolatory rule, which is all we're going to talk about really, the sum of the weights will always be B minus A. Which makes sense because what if your function is a constant function? If I go back up here, f is a constant. If it is, we pull it out of a sum. Now, the integral of a constant function over AB is the constant times B minus A. Well, look at this quadrature rule. If f is a constant, then we factor out the constant, and what's left? The sum of the weights. So those two must be equal. The sum of the weights has to be B minus A. Okay. All right. What that means is f of x is approximated by a polynomial of degree 0, a constant function, which is just going to be f of a plus b over 2. Okay. The actual midpoint rule is going to be the integral of this polynomial. So what we have is the integral is approximately equal to the weight, b minus a, times f at the midpoint. Okay, so that's it. Very, very simple rule indeed. Now, one thing that I mentioned last time, the degree of accuracy of a quadrature rule is the highest degree of polynomial that can be integrated exactly. So the degree of accuracy is 1. So any constant function or linear function can be integrated by this rule exactly. So one thing I want to point out is the degree of accuracy I mentioned before. If you have an n-node rule, the degree of accuracy is at least n minus 1, but in some cases it can be higher. So this is one of the, so here we have a one-node rule. So you think, oh, the degree of accuracy is going to be at least 0, but it turns out to be a little higher. It turns out to be 1. And that's because of symmetry. That the linear function and is not well approximated by a constant function, but the error involved in that approximation when you choose the midpoint. Actually, I think I can quickly have MATLAB plot an example. Okay, so I want to plot. Okay, make sure I have the figure windows going. Okay, so I want to plot a. Let's see. Well, there's an area under the curve thing. So, okay, so I can make something basically a trapezoid. So x goes from 0 to 1, and then up to 1 again, and back to 0 and 0. Okay, and then my y values would be, let's say, 1. I'll explain this in a moment. Okay, y values would be 0, 0, 2, 1, 0. Okay, I'm going to change my axis limits so you can see this a little better. Right now my axis limits are 0 to 1 in x and 0 to 2 in y. So I want to give myself some room here. Alright, so minus 1, 2, minus 1, 3. Okay, so now you can see the trapezoid. Now, what I've done here is I've graphed the function y equals x plus 1 from x equals 0 to x equals 1. So at x equals 0 we get 1, and x equals 1 we have 2. So really the integral is just the area of this trapezoid. So now I'm approximating it by a constant function where the constant takes a value that's at the midpoint. So I'm going to superimpose that on the graph. So I'm going to plot, so at the midpoint, x equals 1/2, my function is equal to 3/2. So I'll put a line through that. So x goes from 0 to 1, and y is 3/2. And I'm going to plot it in a red dashed line. Okay, so the area under this line, this slanted line, I always find it amusing when students refer to a line like this or a line like this as a straight line, as opposed to some other kind of line, because all lines are straight. When they really mean like vertical or horizontal line. So the area under this line, the blue one, is being approximated by the area under this horizontal line. And even though this constant function does a very poor job of approximating this linear function, notice the error in the area. So here we have this triangle I'm tracing out is the error in the area for this half. And here we have the error in the area for this half. They cancel out. So that's why the area under this horizontal line is exactly equal to the area of this trapezoid. But once this function, a linear function here, once we go to even 1 degree higher, like a quadratic, no dice. This is not going to be exact. And really, what do you expect from such a simple approximate integration scheme? Okay. Yeah.
On this midpoint rule, you said there's just one node.
Yeah.
Is that on this on open rules? Because is A and B not considered nodes?
Yeah. Oh, okay. So yeah. So this is an example of an open rule. Yeah. Yes. I meant to mention that earlier. Okay. All right. Yeah, because A and B are not among them. Okay. Second rule, probably the most widely used, trapezoidal rule. Okay. Now, so for the trapezoidal rule, we have two nodes. So this is a closed rule. So x1 is equal to A, and x2 is equal to B. So the only nodes are the endpoints. And then the weights are equal. They're both equal to B minus A over 2. So again, the weights sum to B minus A. So a function is now being approximated by a polynomial degree 1 rather than degree 0. And what is that function? So it's going to be a linear function that agrees with f at the points A and B. So it's equal to f of A, x minus A over, x minus B over A minus B, plus f of B times x minus A over B minus A. So this is a linear function that when you plug in x equals A, this term goes away, and you have A minus B over A minus B, which cancels, and you get f of A. If I plug in x equals B, this goes away. I have B minus A over B minus A, which again cancels to 1, and we get f of B. Now, if I highlight this, can anyone tell me what type of polynomial that is? That we've seen before. Because I said if you plug in x equal A, you get 1, and you plug in x equal what? It's a Lagrange polynomial. So this is one of the Lagrange polynomials for points A and B. This is the other. And honestly, I could have written out this function in many different ways. This is just the one that popped into my head. I could have written it in point slope form also. So I could have written it as f of a plus, okay, so b minus f of a over b minus a, x minus a. So, wait, my dollar signs are off here. Okay, yeah, so that would have worked too. So this is not, it's not point slope form; it's slope intercept form. That would also work. Actually, I'm going to put the slope in square brackets just so it's separated. Point is, it's a linear function that passes through a graph of f at a and b. So, reason why this form is more useful for approximate integration is, but for my quadrature rule, I'm going to have f of a times a weight plus f of b times a weight. Well, the weights are the integrals of these Lagrange polynomials. Now, I'm not going to go to the trouble of working out those integrals. If you really want to, you can for fun. But I'll tell you the result. So, you know what you're supposed to get. Okay, so the approximate integral is equal to b minus a over 2, fa plus fb. Well, actually, you already know what you're supposed to get. If you were to integrate these Lagrange polynomials on the interval ab, the integrals of the Lagrange polynomials are the what? They're the weights. Yeah, so, and the weights are these, b minus a over 2. So the integral of either one of these Lagrange polynomials on ab is b minus a over 2. Okay, so also, nice simple rule for approximating the integral from a to b. Okay. Now, the degree is 1. So we don't gain any more accuracy by adding a node, which is kind of unfortunate. The general pattern here is that, I'll state this formally later, but if we have an odd number of nodes, the degree of accuracy is equal to the number of nodes. If the number of nodes is even, so 2 nodes here, then we have degree of accuracy is 1 less than the number of nodes. Okay, so this is a open I'm trying to get past the italics here. Open 1 node. This is closed and 2 node. Okay. Okay. One more. This is called Simpsons rule. So this is also a closed rule as 3 nodes. So we have x1 is A, x2 is the midpoint, and x3 is equal to B. So it's the union of the nodes from the midpoint rule and a trapezoidal rule. But it turns out the weights are unusual, to say the least. So the first weight and the third weight are the same, so it's b minus a over 6. And then the second weight is equal to 2 times b minus a over 3. So here we have b minus a times 1/6. Here we have b minus a times 2/3 or 4/6. In other words, the midpoint is getting 4 times the weight of the other 2 nodes. But that's what works. So what's happening here is f is approximated by a quadratic polynomial that interpolates f at these nodes, a, b, and a midpoint. So that's going to be fa. So x minus, okay, I'm going to introduce some notation. I'm going to set m equal to the midpoint, a plus b over 2. So we have x minus m, x minus b over...
Wait, x2 equals m?
Yeah, so we're going from left to right. A, m, b. So
Okay.
left, mid, right. Okay. And then a minus m, a minus b, plus f of m, x minus a, x minus b over m minus a, m minus b, plus, okay. Oh, this is going to, oh, come on, don't do that to me. Okay. Plus, okay, f of b times x minus a, x minus m over b minus a, b minus m. So it's kind of long-winded here, but so the integral of this Lagrange polynomial, and this Lagrange polynomial would give the weights. So first one and last one are b minus a over 6. This one, its integral is 2 times b minus a over 3. So the way this rule is written is approximately equal to b minus a over 6 times, okay, so I have f of a plus 4 fm plus f of m plus f of b. Okay, so that is Simpsons rule. So in a way, what you could say that that is equal to 1/3 times the trapezoidal rule, because notice the trapezoidal rule has weights of b minus a over 2 and f of a, f of b, but here it's b minus a over 6. So it's 1/3 times the trapezoidal rule plus 2/3 times the midpoint rule. So if we take a midpoint rule, we have f at the midpoint plus times b minus a. Well, here it's times b minus a times 4/6, or 2/3. So really, it's like the Simpsons rules are a convex combination of the previous two rules. Okay. Now, degree of accuracy is 3. So a free node rule has at least degree of accuracy 2, but because there's an odd number of nodes, we get a boost. So I could plug in any cubic function into in for f of x, in a cubic polynomial, and then this rule will integrate it exactly. Even though it's using a quadratic approximation, it's still exact because of the symmetry. It comes from the equal spacing, and you get a nice cancellation of errors. Whereas degree 4, no dice. It's not going to be exact in that case. Okay, so questions about any of these 3 basic Newton-Cotes rules?
You said trapezoid is the most used.
Yeah, well, that's just my perception anyway. I can't really be certain about that. But one, and the thing is, here we're using one of these rules, interpolatory rules, on the whole of AB. What I'm really referring to is composite rules, where you divide AB into subintervals, and you use these rules in each one. And that's the one I'm referring to. The trapezoidal rule it's very simple to implement, because we have all the weights being equal. You don't have to do anything funny for midpoints where you have like you're basically doing a staggered grid. And also something that will be shown next week for periodic functions, trapezoidal rules have incredibly high accuracy. Now, there are certain cases where the trapezoidal rule is not such a good idea. But someone doesn't really want to bother with mathematical software or anything like that. Just want to quickly implement an approximate integration scheme. Chances are trapezoidal ones and one are going to use, just because it's real cut and dry.
When you talk about dividing the subintervals, do you mean you can use the trapezoidal rule for A to M and then from M to D? Instead of doing this?
Yeah, you can. But what would happen in that case is, so then the rule would have this kind of an appearance, but the weights would be a little different. And actually, that's what instead of having b minus, like instead of 1, 4, 1 in here and b minus a over 6, you'd have b minus a over 4, and you'd have 1, 2, 1. So the midpoint would get less weight. It's also generally less accurate. Yeah. Okay. Any more questions about these 3 rules? All right. Now, okay. Now, how accurate are they really? So in some cases, not all unfortunately, it's not too difficult to come up with a error formula. So the shortest statement I can make about how we get the error is the error in the integral is the integral of the error. Okay, meaning that because what we're doing when we're computing an approximate integral, we're approximating f and integrating that exactly. And so really, this is a consequence of the approximation of the integral is the integral of the approximation. Yeah, how eloquent. In this case, the approximation in question is a polynomial approximation. We're using interpolating polynomial. So since we know the error in the interpolating polynomial, we have a formula for that, then we can integrate the polynomial interpolation error to get the error in the approximate integral. So as an example, whoops, what the hell happened here? Okay. Trapezoidal rule. So the error is equal to the integral, the exact integral, minus the approximation. But the approximation is some linear polynomial P1 that interpolates f at the endpoints A and B. So what that means is, okay, now I can combine these into one integral, f minus P1. But f minus P1 is the polynomial interpolation error. So I'll just fill in what that is. So it's the second derivative at an unknown point over 2 times x minus a, x minus b. So this is directly applying the error formula for polynomial interpolation. So theorem 7.4.1 let me make sure I have the correct theorem number there. Yes. With any... Oh, come on. Okay. Stop that. With n equal 1. And that's what gets us here. So now we have to try to get a handle on what this integral is. Now, we cannot integrate this exactly. Not possible, because f double prime is evaluated at an unknown point, and it's written as c of x because this is expression is being evaluated for all x in AB. For every single x, the unknown point is going to be different. And in any case, we have no idea what it would be. Fortunately, we don't have to, because we're not trying to get the error exactly. We're just trying to get some sort of expression for it, so we get an idea of how big it is. So we use the fact that this expression here, x minus a, x minus b, does not change sign on the interval AB, because at a and b themselves it'll be 0. Now, when inside the interval, x minus a will be positive, x minus b will be negative. So the product as a whole will be negative, and then 0 only at the endpoints. Now, who cares? Well, the weighted mean value theorem for integrals cares. The weighted mean value theorem for integrals, we have the following, that this integral, copy and paste it down there, okay, is exactly equal to, so I can take this part involving a second derivative and essentially pull it out. So for some c in the interval AB. Okay. Okay. So in exchange for evaluating this, now this point was already unknown. So plugging an unknown point in for x just keeps it as unknown as it always was. Nothing's really changed here. So this, whatever's plugged into f double prime, it's some unknown point in AB. Okay. But now look at what's left: x minus a, x minus b. Well, that's known. So that's an integral we can actually evaluate. Okay. Before I do that, I want to recall another mean value theorem. The mean value theorem for derivatives. That's f of b minus f of a over b minus a is equal to f prime of c for some c in the open interval AB. And actually, I could have done the same here. That's something in the open interval. Okay. Now, so this is something that's taught in Cal 1, and we've seen it before in this class too. But if f of x is the antiderivative of g of x, which means that f prime of x equals g of x. Then we have a following. F of b minus f of a is equal to g of c times b minus a. But f of b minus f of a, by the fundamental theorem of calculus, is the integral of a to b of g of x dx. Now g of x is by itself here. So here I can pull out g of x from the integral. So I can really say this is g of c integral of 1 dx. But the integral of 1 from a to b is b minus a. So this is, which is the mean value theorem for integrals. So we have this. So it's really another way of looking at the mean value theorem for derivatives. Now, this is close to what I've used here, except I had this function in here, but it's a function that did not change sign. So the weighted form is the following. The integral a to b fx g of x dx is equal to f of c integral g of x dx. So in other words, if you have an integral of a product, you're allowed to pull out one of the factors evaluated at an unknown point C is in AB, provided that g of x does not change sign on the interval AB. So it's just a generalization of this. So that's really what I've. So this is a theorem that's good to know anyway. It'd be quite convenient for things like error analysis. So that's what I've used here for the trapezoidal rule. That I had this integral, and because this part doesn't change sign, I'm allowed to pull out the other part. Okay. So what remains is evaluating this integral, x minus a, x minus b. So if I go ahead and do that, so I have the integral x minus a, x minus b. Now, what I'm going to do here is yeah, I think I will do that. I'm going to simplify this a little bit. Okay. I'm going to make a change of variable where I'm going to map the interval AB to the interval from 0 to 1. So I have a change of variable u is equal to x minus a over b minus a. So if I plug in x equal a, I get 0. If I plug in x equal b, I get 1. So that means that du is equal to 1 over b minus a times dx. So, all right, so dx is b minus. So now we're going to have here in my integral is b minus a. And then my integrand, x minus a times x minus b. So the way that would work is, okay. I'd be inverting this transform here. So I have x is equal to a plus u times b minus a. So if I plug in u equals 0, I get a. If I plug in u equal 1, I get b. So these two transformations are inverses of each other. So by integrand, which I still have yet to fill in, so x minus a is just going to be u times b minus a. So I'm going to have u times b. And then x minus b, okay, I'm going to fill that in here. Okay, so that's going to be all right, so that's going to be b minus a times u minus 1. Because here I can factor a b minus a out of this. So if I fill in the rest of my integrand, I have b minus, so now I have b minus a again. I actually have two b minus a's here already. So I'm going to put them together. Okay, and then I fill this in here. That's going to give me another b minus a, so b minus a cubed. Okay, and then I have u times u minus 1. Okay, so this integral is equivalent to this one. And I just went through a heck of a lot of calculus to avoid a lot of tedious algebra. And who knows, maybe if I just worked this out directly, I could have possibly saved time, but actually the algebra would have been pretty tedious. So b minus a cubed, integral 0 to 1. All right, so that's b minus a cubed. So I've u squared minus u. So that's going to be u cubed over 3 minus u squared over 2. And I plug in the limits 0 and 1. And that's why I did all this. I don't want to plug in b and a and doing all that simplifying. So I have 1/3 minus 1/2, but that is equal to minus 1/6. So that is equal to, okay, so minus b minus a cubed over 6. Okay, so that part is done. So if I go back up here, this is my error. Sorry, this is my error. So I had this part already. This part, which has worked out to be minus b minus a cubed over 6, although I feel like I'm off by a factor of 2. Nope, it's right. Okay. I was thinking of a different rule that has a different denominator. So if I go ahead and take that result and put that in here, really right here, so So overall error formula is, okay. All right, so the error is equal to minus f double prime at some unknown point, which in the text I use eta, over 12 times b minus a cubed. Actually, I'm going to rename this error label. So I call it E trap. So error in a trapezoidal rule is this, where eta is some unknown point in AB. Okay. Now, so a couple observations. First of all, if b minus a is a large interval, that means the error could be pretty large. Also, notice we have a second derivative. Now, if you have a linear function, the second derivative is 0. So this is another way of seeing that the trapezoidal rule is exact for constant and linear functions. And so certainly if the second derivative is small on AB, then this bodes well for having an accurate approximation. But you have a lot of functions that this rule cannot handle as is. Okay. So questions about how the error was obtained?
Since the error is negative.
Sorry, what?
Since the error is negative, are we taking the absolute value?
Well, yeah, generally you would take the absolute value because you care how big the error is. Most times, but not always, most times you don't care about the sign. Although, F double prime can be positive or negative. Like sometimes it's good to know whether the error is, or whether the approximate integral is a lower bound for the exact value or an upper bound for the exact value. So in cases like that, the sign is helpful. In cases where the second derivative is known to have the same sign on AB. Now, in the book, I have this error worked out for the midpoint rule. Although, because of the problem with the midpoint rule is, and here instead of x minus a times x minus b, I would have x minus m. M is the midpoint. Well, x minus m does change sign on AB. You cannot use the weighted mean value theorem for integrals directly. It can be worked around in a couple different ways, and one of those ways is shown in the book, but it's something that it'll take way too long to get into. So what I'm going to do is show you the error formulas for the other two rules. So the midpoint rule whoops. Okay, so the error in the midpoint rule is equal to, all right, f double prime again at an unknown point, but, oh, whoops, that's supposed to be in the numerator, over 24 times b minus a cubed. Okay. So notice that the error in the midpoint rule is about half as much, even though it has less nodes in here, 1 versus 2. And because second derivative, that means also exact for linear functions. And finally, Simpsons rule. Okay, so here we have minus f fourth derivative over 90. Okay. To the fifth power. So fourth derivative, which means it's exact for cubic functions, and here's times b minus a to the fifth power instead of cubed, because of a higher degree of accuracy. Okay. All right. Now, So general remarks about Newton-Cotes rules, because I've only shown you Newton-Cotes rules for, closed 2 nodes, open 1 node, closed 3 nodes. So you can have Newton-Cotes rules for any number of nodes, and you can make them closed or open. Okay, now. Okay. So actually, I'll make my comments down here. So for general n-node Newton-Cotes rule, closed or open, we have a following. The degree of accuracy is n if n is odd, and n minus 1 if n is even. And that's what we've seen here. Here we have n, the number of nodes being 2, its degree of accuracy is 1. Here we have n equals 1, degree of accuracy is 1. Here we have n equals 3, degree of accuracy equals 3. Okay. All right. Now, so one might think, okay, we've already seen as we go from 2 nodes or 1 nodes to 3 nodes, we have a much higher degree of accuracy. And Simpsons rule is quite effective for a lot of functions. So why not go further? And we know how to work out the weights. It's the integrals of Lagrange polynomials. Why not just keep going and use larger number of nodes and presumably get more accuracy? That as n increases, some weights become negative. So in fact, for n greater than or equal to 11, there's no n-node Newton-Cotes rule with all positive weights. And in fact, I've seen cases where n is less than 11, like around 8 or 9, where you start to get negative weights. And what may be happening is that I would just try like a closed rule, for instance, as the easiest one, but maybe some kind of open rule where so you pick whatever first and last nodes that are in the interior, and then you make them equally spaced, and maybe still be able to get positive weights. But once n becomes 11, there's absolutely no way to get all positive weights. So never use a Newton-Cotes rule with this many nodes. You're just going to get a bad result. Okay, so that's related to the problem with high degree polynomial interpolation with equally spaced points, that leads to Runge's example. You're trying to evaluate the integral of f by integrating exactly a poor approximation of f. So your approximate integral is also going to be poor. Okay. All right, so those are often referred to as basic Newton-Cotes rules. And what's meant by that is not about ease necessarily, but simply that, okay, I'm using the wrong words here, but anyway. All that's meant by word basic here is that we're taking the interval AB and we're just applying the Newton quadrature rule to that with equally spaced nodes, as opposed to trying to like dividing AB into subintervals. So, and that's where it leads to composite rules. Okay. So where'd it go? Composite rules. So the error in Newton-Cotes rules can be quite large for two reasons, really. If the interval AB is large, or higher derivatives of f are large. Because notice the rules that the error formulas that I showed you have either a second or fourth derivative, and what if those are large on the interval AB? Then you're bound to have some large error there. So what can be done about that? So instead, can use composite rules. So the idea behind composite rules is divide the interval AB into n subintervals of width h equals b minus a over n. Okay. So now, instead of your error being proportional to a power of b minus a, it's going to be proportional to a power of h. But if you choose a large number of subintervals n, then h is going to be nice and small. So then what you do is apply a quadrature rule, such as Newton-Cotes rule, on AB. Now, I'm going to talk about composite Newton-Cotes rules, but you can really apply this idea to any quadrature rule, including some of the others that we'll see later in this chapter. So you just divvy up AB into subintervals. Here, I'm making them equally spaced, just for convenience. And I don't recall, I want to see what else I have planned to be covered. Okay. I should look here. Okay. Unfortunately, no. I will cover more sophisticated integration techniques next week, but so one in particular is called adaptive quadrature. That's something I didn't have room in the schedule for, where you end up using unequal subintervals of unequal width in such a way that where a function is smooth, nicely behaved, you can use a larger interval. Where it's oscillatory or steep, large derivatives, you use a smaller interval. So it tries to figure it out in a sophisticated way. And a lot of mathematical software implements that for reliability. But here I can talk about cases where we use subintervals of equal width. Okay, so here are the composite versions of the Newton-Cotes rules that I just showed you. So the composite midpoint rule. Well, actually, before I lay out the rules themselves, so we let interval AB be divided into n subintervals of width h equals b minus a over n, and with endpoints xi minus 1 to xi for I equals 1 to up to n, and xi is equal to a plus I times h. So these are the nodes that we're going to use, a plus ih. In this case, we're working with okay. So x naught is a left endpoint. X naught is equal to a, and xn is equal to b. And then x1, x2, x3, and so forth are the points in between, separated with spacing h. Okay. All right, so the composite midpoint rule is that the integral okay, so that would be 2h times f of x1 plus f of x2 plus and so on fxn minus 1, where is even. Whoops, something went wrong here. Okay. So really what's happening is you can think of AB as being divided into intervals of width 2h. So the first subinterval starts at x naught, which is a, and ends at, oh, I'm sorry, I have a typo here, x3. Okay. So I'll just type this out here. So the first subinterval with 2h and endpoints x0, x2, and midpoint x1. Second subinterval is also width 2h. They all have width 2h. Endpoints x2, x4, midpoint x3, and so on. So you can think of AB as dividing into intervals marked off by the even-numbered points, and therefore the odd-numbered points to be the midpoints. And that's what actually gets plugged into F. So really, we're only plugging in half the points that we have, roughly, into F. Okay. And then, okay. Also, I will give the error. So the error, I'll show this more closely for trapezoidal rule, but the idea behind the error in composite rules is you have the error formula for each subinterval that you use. So then you just add up those errors, and then you try to simplify that expression as much as you can. And there is some simplifying you can do. So for midpoint rule, it turns out to be, F double prime at an unknown point over 6 times b minus a times h squared. Therefore, this rule is second order accurate. Because the error is big O of h squared. So in other words, if I double the number of subintervals, the error should decrease by a factor of 4 because of a squared. Okay, so it's nice to have some high order accuracy there, but the error should decrease fairly quickly if we increase the number of points. But if you increase the number of points, that makes the rule less efficient. So that's one thing to keep in mind. Okay. Now, but I want to point out this is on n over 2 subintervals of width 2h. Now, I did that, even though that's not what I have here, just because it's easier to write out what it is. But the rule can be redefined in such a way that using n subintervals, what we have is the exact integral is equal to this midpoint rule. So it would be a sum f at the left endpoint of each subinterval plus h over 2. Not sure if that extraneous space got in there. Okay. So here it's the same idea. We have an interval of width h. So we've taken midpoint of that by taking a left endpoint plus half the width. So h over 2. And in that case, the error is going to be f double prime at an unknown point over 24 times b minus a h squared. So that changes the constant, because here we're using twice as many subintervals. So if we, half as many subintervals. If we double the number of subintervals, because it's second order accurate, the error should be cut by a factor of 4, and sure enough it is. Okay. So notice we only have b minus a to the first power. So that's not going to unduly influence the error if the interval AB is large. Okay, so that's a midpoint rule. Composite trapezoidal rule Okay, so here we have okay. So I have h over 2 times f of x naught plus 2f of x1 plus 2f of x2 and so forth, all the way up to the second to last node plus f of xn. Okay. So notice what happens is we plug in all the nodes, x naught up to xn, so n plus 1 points altogether, these are the endpoints, into f. And then we add them all up, but with different weights. So every point has a weight of 2 in here, except the endpoints, where I have a weight of 1. And then we multiply the whole thing by h over 2. Now, where that comes from is the fact that we're approximating the area under f by the area of a bunch of trapezoids. Now, what's the formula for the area of a trapezoid? It's going to be the average of the heights times the width. Well, the width of each trapezoid is h. The height, you'll have f of x naught for the first one on the left, and then f of x1 on the right, over 2. Second trapezoid, f of x1 again, f of x2, so left and right, divide by 2, and so on. The point is, each one of these in the interior is used by 2 trapezoids. It's shared between them. That's why it gets a coefficient of 2. F of x naught, f of x1, f of x naught and f of xn are involved in only one trapezoid, so they have a weight of 1. Okay. Now, and actually this could be written as a summation. Okay, so I have f of a plus 2 times the sum fxi plus f of b. Okay, so that's another way that this rule is written. You see how we coded MATLAB. You're summing up these f values and then just tacking these on and scaling by h over 2. What's interesting is there's another name for the composite trapezoidal rule called the improved ties method, TAI. A biologist by the name of Mary Tai published a paper where she needed to do something else, essentially computing the area under the curve, and claimed to have invented this method. Actually, she invented some other method first, which I'm not sure what it was, probably Riemann sum, and called that Tie's method. And then thought better of it to use trapezoids for more accuracy, and called that improved Tie's method. She had no idea of the long-standing existence of this rule, being a biologist, I guess, and that name has gotten out there as the improved Tie's method. So, yes. So like I said, naming methods is a funny business, and I was not exaggerating. So, okay. Now, what about the what about the error? I know my time is running out. Well, okay. I'll quickly state the other one, Composite Simpsons. Come on, Simpsons rule. Okay, so that has a very similar appearance as the composite trapezoidal rule, but the weights are different. So h over 3 out front, and then x naught plus 4 fx1, which comes from a 4 in the basic Simpsons rule, and then 2 f of x2, because f of x2 is the right end of one piece and the left end of another piece. Again, it's being shared by 2 applications of Simpsons rule. And then, yeah, so then we go, so left, midpoint, right, left, midpoint, right, and so forth. Okay, so 4f of x n minus, actually I'll do this, 2 f x n minus 2. Hello, what's going on here? Stop that. It's being uncooperative again. Plus 4 f of x n minus 1 plus f x n. Okay, that's it. Yeah, so 1, so the weights, 1, and then 4, 2, 4, 2, 4, 2, etc. 2, 4, end on a 4, and then 1. Now, I should mention this requires that n is even for this. Okay. And then the error, okay, is minus fourth derivative, okay, over 180 times b minus a times h to the fourth. So fourth order accurate. So if you double the number of subintervals, h gets cut by a factor of 2. The error should get cut by a factor of about 16. It doesn't always happen, but in most cases it does. Okay. I haven't stated the error formula for trapezoidal rule yet because I'm going to show you where it comes from. Okay. And then a similar procedure can be used for the other two. Okay, so this is the error in the composite rule, trapezoidal rule, or improved ties method. Add up error in basic trapezoidal rule over all subintervals. So the way this works is, okay. All right, so what we have here is a sum over all the subintervals of the error on each one. So we have minus f double prime over some point, which I'll call eta I, over 12, okay, times, now the basic trapezoidal rule had b minus a cubed, but that's going to be h cubed here because that is the width of each subinterval. So now I'm going to factor out what I can. That's the h cubed over 12. Okay. Or 12, not 2. But then what I'm going to do is I'm going to throw in a fraction here, n over n. You'll see why momentarily. And then the sum of f double prime at these unknown points. Now, each unknown point is in its own subinterval, but they all belong to AB. We know that much. Okay. Now, I'm going to take the n in the numerator and associate it with, okay, so I still have a 12 down here, and then I'm going to have h squared times n times h. So I'm taking one of the h's from here and lumping it in with the n. And then the other n, I'm going to have still a separate fraction. And then the sum. Okay. Now, if you recall how h was defined, h is equal to b minus a over n. So if I multiply both sides by n times h is b minus a. So now I can have h squared times b minus a over 12. And what about this? If I'm summing n items and dividing by 1 over n, what is that? What?
That's the mean of the average.
Yeah, it's the mean or the average of these values. Now, if we assume that f double prime is continuous on AB, then by the intermediate value theorem, f double prime is equal to its own average of these values somewhere on AB, because the average would be an intermediate value to all of these. Okay. So I can replace this with f double prime at some unknown point eta in AB. Okay. So the intermediate value theorem is something that can be used to justify that replacement. Okay. So that's where the error formula comes from. So it's a similar form to that of the midpoint. H squared b minus a second derivative over a constant. It's just that the constant is 12 instead of 24. So the midpoint rule, composite version, again, is generally twice as accurate as the composite trapezoidal rule. Now, the last comment I want to make is these error formulas can be used to find n to achieve desired accuracy. And this is an example 941. So what's done in that example, I'll just give a quick rundown. If I take this expression, or at least its absolute value, and I say I want that less than some tolerance, like 10 to the minus 3, something like that. Well, I have b minus a, 12, and h. All of this, well, actually what I could do is I can express, like if I don't know h yet, I'm trying to choose n, which would give me h. So what I can do is I can express this in terms of n. And if I know how big this can get on the interval, then if I set this to be less than some tolerance, I have an inequality that I can try to solve for n. So I think it would take too long to type it out, but I do have it here. All right. So for example, here, I'm approximating this integral, and I want this error bound, 10 to the minus 3. So here's the error for trapezoidal rule. And what I do is I fill in the second derivative at an unknown point, and I express b minus a h squared in terms of n. So I get this n squared in the denominator. So then when I work on this, keep in mind eta is between 0 and 1. So now I have e over 12n squared is less than my error tolerance. So I get to this inequality, and now I can rearrange and get a value for n. So in this case, what this means is, if I choose n to be at least 16, the error will be guaranteed to be less than 10 to the minus 3. And I think what I carry out in this example, okay, I don't do that here. But this is an upper bound. So in fact, chances are the error will be a lot less. But again, you're getting a guarantee of accuracy. I do the same thing in Simpsons rule for the same integral. So now I have n to the fourth in the denominator because I have b minus a h to the fourth. So now, working it out the same way, I get this result, that n must be at least 2. But that's just the basic Simpsons rule. And that gives you an idea of how accurate Simpsons rule is. In a lot of cases, not necessarily all cases, compared to the other ones. Because it's fourth order accurate versus second order accurate. Okay. I'm sorry it wasn't time for homework questions. I had to get all this covered. But if I look at what's happening coming up, okay, so this is what's coming up next time. Okay, but I'll try to make sure that there's time for homework questions. If I recall that this, a whole lot of you had none to ask last time. So I haven't gotten much in the way of email questions either. So be sure to keep those coming, and you help yourself and you help your classmates. And hopefully we'll also see some homework coming in soon. So. Okay.
I do have questions.
Okay. I should not keep everyone else, but if people are welcome to stay or leave, but go ahead and ask. I'll keep it recording.
9.1.1.
911. Okay.
You said we should use the example, the approaching example 9.1.2.
Right.
But the formula you gave there, is this that same formula for approximation you're using? Because earlier in the textbook, you said when we have equally spaced points that are symmetric.
Yeah.
And that is the center difference formula.
Right.
Are we using the center difference formula?
It will be a center difference formula. So when I say use the approach in this example, it's important not to take that too far. And I say only the approach. Because the approximation for a problem it'll have these 3 points, but also coefficients times f of x naught minus h and f of x naught minus 2h. So because you have that symmetry in the points that are used, it will be a center difference. Okay. Yeah. So whereas here you had 4, in the example there were 2 Taylor expansions, but now you'll have 4.
Then 9.1.4.
9.1.4. Okay.
I don't understand that the index when you say I starts from minus j.
Okay. So what I'm doing here, if we look at the formula you're supposed to use, this one right here. So this is because we have some of these points are to the left of x naught and some are to the right of it. It gives a convenient way to define those points. So, here there's no specific definition given, but in the problem there is. So what that means is, okay. So all the indices from minus j up to minus 1, 0, 1, 2, up to k. Every integer in between. And that allows you to fill in this for the definition of xi in here. What I would suggest doing is trying it out on an example. And actually, probably the best example would be the one from 9.1.1, where you have j and k both equal to 2. And if you'll see what this product becomes, and give you an idea as to what it simplifies to.
Lastly, 9.1.5.
Okay. All right.
So you talked about the MATLAB function. Is that the one you said you posted? Because that you said make like range.
Oh, shoot. I posted the wrong one. Hold on. Oh, wait. It should be over here. Oh, yes. It's... Oh,
So is it the same thing?
Oh, okay. Make Lagrange is needed for a different problem. Yeah, I will I will post this. Okay. Okay, and actually, I think I. Okay, I actually want to check the problem here. 912. Okay. Oh, okay. So I have that. All right.